in this problem, what I give you is I give you just a set, a list. So I've listed out in roster format a list of real numbers. In fact, they're all rational numbers. And it's the set of all rational numbers that are a unit fraction less than 1. So it's 1 minus a half, 1 minus a third, 1 minus a fourth, 1 minus a fifth, 1 minus a sixth, and so on. And so the claim that we want to establish is that no matter how small of an epsilon that I pick, so for any epsilon greater than 0, we can find an element of this set, in other words, a rational number that's a unit fraction less than 1, that satisfies the absolute value of x minus 1 is less than epsilon. So first of all, how do you understand this claim using the definition of a distance function? What did you say for this prompt here? How do we understand this as a claim about distances? Yeah, Hallie. Right, so over here where we have the absolute value of x minus 1, anytime you see the absolute value of a difference, what we're really doing, the whole reason that we do such a thing in analysis, is that we're measuring the distance between what? Between x and 1, and x here is an element of our set, right? So the first thing we might do is look at this, this portion, the absolute value of x minus 1 is less than epsilon, and say the distance between x and 1, distance between x and 1, is less than epsilon. But then here in this problem, x represents an element of our set. So what I might say is I might just replace the word x here, distance between that element of u, and use this there exists statement here. There is, that's an existence statement. So there exists an element of u such that that element is within is within epsilon units of distance of 1. So if I want to finish the sentence here, no matter how small epsilon is, there exists an element of u such that the distance between that element and 1 is less than epsilon. Now remember, when we first were introduced to epsilon several weeks ago, I like to think of epsilon when we use that notation in analysis. We usually use it to represent a quantity that can be as small as we like. So I might even take this a step further and kind of take this distance as less than epsilon and rewrite this to say the distance between that element and 1 is as small as we like. Okay. So here's the picture that I'm trying to set up. Here's the picture that exists in my cartoon bubble when I think about this. So the set U is really just a set of real numbers. What I've done here is I've depicted at least a few of the members of this set as just points on the real y-axis over here. So here's 1/2, here's 3/4, 1/2, 2/3, 3/4, 4/5, and so on and so on and so on. Right? So what the statement that we're trying to prove is really saying in a geometric way, so in a way that I can sort of draw a picture, is that if I pick a value for epsilon, and that value can be as small as we like, let's suppose I pick epsilon equals 0.1 or something, then what that says is I should be able to find one of these green points, and I've only graphed the first 13 of them, so there's infinitely many, but I need to be able to find one of those green points that's within a 0.1 distance of the number 1, and the number 1 here is right there on the y-axis. So to be within 0.1 of 1 means I need to be between 1.1 on the one hand and 0.9 on the other hand. Right? So what I've done here is I've set up a little radius, epsilon equals 0.1. That's the distance between 1, which is supposed to be this central point that we're trying to get closer to, and then the outer limit here is going to be 1.1 on the top side and 0.9 on the bottom side. And so according to this picture, how do I know that there exists an element of this set that has a distance less than 0.1 to the number 1? The green points are my set. And sure enough, at least one of those points actually is within this interval. So maybe just to make my point a little clearer, what we're doing is asking, do these green points eventually traverse their way into that red shaded interval? Okay. That's the interval of points that are less than 0.1 units away from the number 1. And sure enough, the answer is yes. We can find at least one point. So here's our x in U that satisfies the absolute value of x minus 1 is less than epsilon for this value of epsilon, right? And so, at least for that value of epsilon, the answer is yes, there exists such an element. But what's the tricky part about epsilon? It can be smaller, right? We don't have to be satisfied with 0.1. 0.1 is not really that small of a real number in the grand scheme of things. We can always make it smaller, right? And so the trick of this definition, and the trick of the definition of a convergent sequence that we'll see after the quiz today as we make our pivot, the trick is that this needs to still hold even if I pick a much smaller value for epsilon. So let's say epsilon equals 0.01. So I've made it 10 times as small. Now my little interval on the real line is going to be much smaller. And so the upper limit is going to be 1.01. The lower limit is going to be 0.99. And again, I need to know, is there one of these elements of our set that exists in this little red interval? And I haven't plotted enough of these points yet to be sure of that, because I've only plotted the first 13 elements of the sequence. But if I keep going, 14, 15, 16, 17, 18, 19, 20. I don't know why it's not updating here. 7, 28, 29, 30, 31. Oof, man. I have to actually go pretty far up to 43, 44, 45. Whoops, 45, 46, 47, 49, 50. I wish there were a quick way to do this. 59, 60, 61, 2, 3, 4, 5, 6, 7, 8, 9, 70, still going. Again, as soon as I find one that's greater than or equal to, the greater than 0.99, then we can stop. Uh, 90, 1, 2, 3, 4, 5, 6, 7, 8, 9, 100. Oh, okay, great. So that took a while. And in fact, so in order to find a value, in order to find one of the elements of this set, which was actually within a 0.01 distance, we had to go way, way far out into in fact, the 100th element of this set. But it exists, right? And so our hunch is that what we'd like to prove in this problem is that that can always happen. And on this problem, we're thinking about these numbers just as a set. So we're just thinking about it as the collection of green dots on the real line. But the shift that we want to make after the quiz is we want to begin to bring in some heavier duty technology. And by technology, I mean theorems. That can help us to establish claims like this. And what's going to help us is that instead of just thinking of it abstractly as a collection of real numbers, what we're going to do is be able to order this collection and actually say this element here is the first element of a sequence. This is the second element of a sequence, third element, fourth element, and so on. So that gives us a way of kind of understanding these not in isolation, but in their relation to one another, which is nice. And in that viewpoint, instead of thinking of this as just a collection of points on the real line, we're going to think of it as something that's more akin to kind of a graph of a function. And then we might ask about that graph, is it true that however close I want to get to the number 1, that I can get there if I go far enough out? And it sure looks like for this sequence, that answer is yes. Right? That if I zoom in on 1 right here, keep zooming in zoom in one more time, so that now my grid lines here are counting by 0.02s. Sure enough, my point right here, the 100th element, is within 0.01 of the number 1. So thinking about it as a sequence rather than as a collection of isolated points is going to be what we do when we take the turn into our 5th packet.